Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're continuing our lecture on chapter 4 and we made it to the 5th objective. Now here we want to elaborate on acids and bases so we can better understand how to categorize strong from weak acids and bases. Now there are many different ways to define acids and bases, but we're going to focus on the Arrhenius definition here in this chapter. Now the Arrhenius definition describes an acid as a substance that increases the concentration of H plus or hydrogen ions in aqueous solution. An Arrhenius base, this can be described as a substance that increases the concentration of hydroxide or OH minus ions in aqueous solutions. Now, there are 7 strong acids and 8 strong bases that we need to commit to memory. So let's go over these lists, starting off with strong acids. The list of strong acids is hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, perchloric acid, and chloric acid. These are the 7 strong acids that you should commit to memory. Then we have a list of 8 strong bases. We have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So again, this is a list of 7 strong acids and 8 strong bases that you should remember. Now, the next thing that we want to talk about in this objective is salts. The word salt is a general term that can be applied to many different ionic compounds, and there are 2 ways that we can define a salt. The first way is that a salt can be thought of as an ionic compound whose cation is not H plus and whose anion is not hydroxide. But a better definition is that a salt is the product of an acid-base neutralization reaction. Any salt that dissolves in water is a strong electrolyte. However, not all salts dissolve in water, so it's going to be really useful to be able to predict a salt's solubility. This chart right here summarizes some of the important things to keep in mind in regards to our solubility rules. Let's go over this because this is going to be extremely important for the rest of this chapter. There are 2 categories. We have soluble ionic compounds and insoluble ionic compounds. Let's go ahead and get started with this first category, soluble ionic compounds. So for the first rule here, all group 1 cations, so lithium, sodium, potassium, rubidium, and cesium, all of these are always soluble. Group 1 cations are always soluble. That's the first rule for soluble ionic compounds. Then we have here ammonium. Ammonium is also always soluble. Then we have this category here where we have nitrate, acetate, and perchlorate, and for these 3 anions, they are always soluble. Then our next category, we have chloride, bromide, and iodide, and the rule here is that they are soluble unless they are paired with silver, lead, copper, or mercury. All right, unless they're paired with silver, lead, copper, and specifically copper 1 and mercury 1, then they are not soluble. So again, chloride, bromide, iodide are soluble unless they're paired with any of these 4 cations. Wonderful. And then the last rule here, all right, this is sulfate. It is soluble except if it's paired with calcium, strontium, barium, silver, or lead, then it is not soluble. Okay, so that is our soluble ionic compound rules. On to our insoluble ionic compounds. What are the rules here? Well, metal hydroxides, they are always insoluble unless they have a group 1 cation or they're paired with calcium, strontium, or barium cations. Then they are soluble. The next category here, we have carbonate and phosphate. They are insoluble except if they're paired with group 1 cations or ammonia. And then last but not least, we have sulfide. This is insoluble except when it is paired with group 1 cations or group 2 cations or ammonium. Then it will be soluble. So these are our rules. We should definitely commit these rules to memory. They're going to be important when we talk about precipitation reactions in the next objective. With that, let's go ahead and also do some practice problems that are going to help us make sure we understand the solubility rules for ionic compounds in water. Okay, so this problem says, determine if the ionic compound is soluble or insoluble. Let's look at our first example here. All right, this first example, potassium sulfate. Is this soluble or potassium sulfate? Is it soluble or insoluble? Okay, what do we have going on here? We have potassium cation, we have sulfate anion, all right? Sulfate anion. This has a 2 minus charge. Okay, let's go back and refresh our memory on the rules for potassium, cation, and sulfate anion. So if we go back to our table here, I'm going to do a little bit of erasing so that we can highlight what we really want to focus on and work from there to determine whether potassium sulfate is soluble or is not soluble. Okay, so potassium, we can find that. All right, it is right here. It's a group 1 cation. Those are always soluble. All right, those are always soluble. Now, in addition, we could also look at sulfate really quickly. This is always soluble unless it's paired with any of these 5 cations. Potassium is not part of this list. So both of these are, under these conditions, soluble. All right. Potassium is always soluble, and so even from just this, potassium is from group 1, and all ionic compounds containing group 1 cations are soluble. And just as a further confirmation, sulfate is also soluble when it is paired with potassium. Wonderful. Let's look at another example here. All right, we have sodium sulfide. Okay, we have sodium here and sulfide. All right. S2 minus. Let's go back to our table and look for sodium and sulfide. What is the rules here? Well, we can find sodium right here. It is part of the group 1 cations. And like we said, since sodium is from group 1 and all ionic compounds containing group 1 cations are soluble, that means sodium sulfide is soluble. Now, what if you looked at the sulfide anion first? Would you have been able to determine that sodium sulfide is soluble? And the answer is, of course, yes. So if we were looking at sulfide first, it says that sulfide is insoluble unless it's paired with a group 1 cation or a group 2 cation or ammonium. And guess what? Sodium is a group 1 cation. So sulfide would actually be soluble in this condition. And so we were correct in saying that sodium sulfide is soluble. All right, our next example is lead 2 chloride. All right, so we have lead 2, okay, and we have chloride. Okay, let's look at our rules for chloride anions. All right, here's chloride. Chloride, bromide, iodide, these halogens right here are always soluble except except if they're paired with silver, lead, copper, or mercury. And guess what? Here in this example, chloride is indeed paired up with lead, which means that it is no longer soluble. It is insoluble. So chloride compounds, while they're usually soluble, the exception is when the cation is lead, which it is here in this example. So this ionic compound is insoluble. Okay, this next example is calcium chloride. All right, we have calcium and we have chloride. Calcium and chloride. Let's look at our table for hints. Okay, chloride again here is soluble, except if it's paired with silver, lead, copper, or mercury. In this example right here, calcium chloride, chloride is not paired with any of those. It's paired with calcium. And therefore, it sticks to its original rule. Compounds containing chloride are usually soluble. And so this ionic compound is soluble. Wonderful. Let's move on to our next example. This is zinc sulfate. Zinc sulfate. We have zinc, all right, and we have sulfate. All right, let's think about this. Sulfates, if we go back here, sulfates are usually soluble, except when they're paired with calcium, strontium, barium, silver, and lead. None of that list includes zinc, which means we can confidently say that this ionic compound that contains a sulfate is soluble. So zinc sulfate is soluble. And then on to our last and final example, aluminum hydroxide. We have aluminum and we have hydroxide. All right, looking back at our rules for metal hydroxides is that they are insoluble, except when they have a group 1 cation, calcium, strontium, or barium. Okay, well, aluminum is not part of the exception list. So that means this metal hydroxide is insoluble. And with that, we have completed our set of practice problems for acids and bases and our solubility rules. Now we're going to go ahead and move into Objective 6, which is all about precipitation reactions. A precipitation reaction occurs when two solutions containing soluble ionic compounds combine to form an insoluble product called a precipitate. Now, precipitation will occur when two ions in solution are so strongly attracted by electrostatic forces that they form a product that now does not dissolve in water. And the key to predicting and understanding precipitation reactions lies in the concept of solubility and insolubility. Solubility is a measure of how much of a particular substance can dissolve in a solvent to form a homogeneous mixture at a given temperature and pressure. Insoluble substances do not dissolve in the solvent and thus can form a precipitate. Now, the solubility rules we covered in that previous objective is going to help us determine this when we work with problems. And the key is this, all right? This is the main takeaway. When two solutions of ionic compounds are mixed, the cations and the anions interact. And if a combination of cation and anion forms an insoluble compound, as dictated by the solubility rules we covered, then a precipitation reaction has occurred. Now, on this page, we see an example of a precipitation reaction. Let's work through it to understand why it is a precipitation reaction and what the precipitate is. So what we're looking at here is silver nitrate and sodium chloride react together. These are the reactants. And what they're going to form is silver chloride and sodium nitrate. Now, what you notice here, looking at this example, is that there has been kind of a swap of cations and anions here. So the silver is now paired up with the chloride in the products, and the sodium is now paired up with the nitrite here in the products. So we have this kind of double displacement. We're going to talk about that here in a second. All right, now looking at these two reactants, silver nitrate and sodium chloride, based off of our solubility rules, both of these are soluble. All right, both of these are soluble. And we denote that with this kind of aqueous label here for both of these reactants. What they form is silver chloride and sodium nitrate. Now, sodium nitrate, based off of our solubility rules, this is soluble. All right, and again, we give it this aqueous label. Silver chloride, however, this is insoluble based off of our solubility rules. This is going to be the precipitate. This will not dissolve in water. And so what we have here is an example of a precipitation reaction. The silver chloride is insoluble in water and it precipitates out of the solution. Now, what this illustrates is that precipitation reactions are examples of what is called a double displacement reaction, in which the reactants exchange ionic partners. And so therefore, we can predict when a precipitation reaction will occur by exchanging the ionic partners and then checking the solubility of the products to determine if there is an insoluble product, and thereby concluding that this is a precipitation reaction and that insoluble product precipitates out of the solution. With all of this information, let's develop a kind of system to help us, all right, to predict whether precipitation will occur when two solutions are mixed. We're going to follow these steps. First step is we're going to write down the formulas of the ionic compounds being mixed. Second rule, on the right side of the arrow, write down the ionic compounds you would get if you swapped ionic partners. When you write the formulas for these compounds, be sure, of course, to balance the charges of the cations and anions so you get neutral compounds as your products. All right, then the third rule, if necessary, add coefficients to balance the equation. All right, and then the fourth rule is use the solubility rules to determine if the compounds on the right side of the reaction arrow, aka the products, are soluble or insoluble. If something is soluble, again, you add the label aqueous, AQ, to it. And if it is not soluble, if it is insoluble, write S or solid next to it. If one of the products is a solid, then the solid will precipitate out, and you have a precipitation reaction. If both of the products are aqueous, then in the realm of precipitation reactions, we don't have a reaction that's occurring. All right, with that, let's go ahead and do an example problem. Let's see if we can get the hang of this. This example says, will precipitation occur when an aqueous solution of copper 2 sulfate is mixed with an aqueous solution of calcium chloride? So this is a really great problem. It takes into account a lot of things we've learned up to this point in our general chemistry course. Let's write out copper 2 sulfate. We have copper 2 sulfate. All right, we're forming a ionic compound from these two ions. This is going to write out as copper sulfate like this because we exchange these charges. You get copper 2 sulfate 2, but you want to write this in its smallest form, so without the 2's here. All right, so this is copper sulfate. It's aqueous based off of the problem. And then we also have this react with calcium chloride. Swap these out, we get CaCl2. Okay, so we figured out what copper 2 sulfate looks like, and we figured out what calcium chloride looks like. Those are our two reactants. Let's go ahead and write them out. So we have copper sulfate plus, and actually make sure to write aqueous here, plus calcium chloride, also aqueous. All right, so we went ahead and we did the first step. We wrote down the formulas of the ionic compounds being mixed. Now for the second rule, on the right side of the arrow, we want to write down the ionic compounds we would get if we swap ionic partners. So what that means is this copper is no longer paired with sulfate, but it's going to be paired with chloride. What kind of product does that give us? That gives us copper chloride. Okay, and we don't know if it's aqueous or not yet. We have to figure that out in the next steps. All right, and then that means also that calcium is no longer paired with chloride anymore. It's going to be paired with sulfate. So this is going to give us calcium sulfate. All right, so these are our two products that formed from swapping ionic partners. All right. Now we wrote these out. We made sure to balance the charges. You guys can double check on your own. The charges are balanced here for copper chloride and calcium sulfate. Now, if necessary, add coefficients to balance the equation. Looking at this, it already looks pretty balanced, so we are good to go. Now we can move into that fourth rule. Fourth rule, we use the solubility rules to determine if the compounds on the right side, on the product side, are soluble or insoluble. So let's go ahead and take a look first at copper chloride. Okay, we have copper chloride. Is this soluble or not? Now, chloride is always soluble except if it's mixed with a couple of cations. Let's go back to our table and check if copper is one of those compounds that would make chloride insoluble. Okay, let's go back all the way here to the table. Chloride, always soluble, except when it is mixed with silver, lead with a 2+ charge, copper with a +1 charge, all right, or mercury. Okay, so let's go back here. We have copper chloride, and here we have copper 2 chloride. This is such an important distinction to make. This is not copper +1. This is copper +2 or 2+. All right. And so this is actually very much soluble. And so we give it the label aqueous. Wonderful. Let's look at the other product now. All right. Let's look at this. Calcium sulfate. Is this soluble or not? Okay, we have sulfate here. Sulfate is typically soluble, but there are exceptions to the rule. Is calcium an exception that would make this insoluble? Let's go back to our table and triple check. So sulfate is soluble except when it is paired with calcium, strontium, barium, silver, and lead with these specific charges. And notice calcium is part of the exception list, calcium 2+, which is what we have. And so actually this sulfate compound is indeed insoluble because it is paired with calcium 2+. And so we give this label an S. So now we move into Rule 5. If one of the products is soluble, then that solid will precipitate out. This calcium sulfate is going to precipitate out. We have a precipitation reaction. A precipitation reaction will indeed occur. All right, and that's that example. Let's go ahead now and move into Objective 7, describing reactions in solution. In this objective, our main discussion is net ionic equations. One useful way to represent a reaction occurring in aqueous solution is by writing the net ionic equation. We looked at an example in the previous objective about a precipitation reaction. We're going to revisit that exact reaction here again. So if you remember, we had silver nitrate reacting with sodium chloride to give us silver chloride and sodium nitrate. Now, this right here, we have the overall or the formula equation for this reaction, also sometimes called the molecular equation. Here we see all of the reactants, we see all of the products. Although the formula or the molecular equation shows the reactants and the products of the reaction, it does not give a correct picture of what actually occurs in solution. Actually, what is called the complete ionic equation does a better job at representing the actual form of the reactants and products in solution. In solution, these reactants are going to be dissociated. You're going to see that you're going to have silver cations, nitrate anions. You're going to have sodium cations, chloride anions. You're going to have sodium cations in the products, nitrate anions in the product. This insoluble silver chloride, however, this does not dissociate, so it stays the same. And so here in the complete ionic equation, all substances that are strong electrolytes are represented as ions. That is what is written here. This insoluble compound, this is written in full. It is not written as two different ions, two dissociated ions. Now, what we can do next is, knowing that the complete ionic equation reveals that only some of the ions participate in the reaction, the ions that aren't, those are called spectator ions. We can begin to eliminate ions that are present in both the reactants and products. Those aren't really participating. This sodium that appears in both the reactant and product, this is a spectator ion. We can eliminate it. So can we do the same for the nitrate? We can eliminate that. It appears in the products and the reactants. It is a spectator anion. And that means what we're left with, all right, is the ions that are actually participating in the reaction. And we can now write the net ionic equation, which includes only those solution components undergoing change, no spectator ions included. Those spectator ions, again, are those ions that appear in the reactants and in the products. You can eliminate those when you are writing the net ionic equation. And so the net ionic equation for this reaction is silver cations plus chloride anions give us silver chloride. All right. So in summary, we just learned how to get to a net ionic equation. We first wrote the formula or the molecular equation. This is the full equation. All the reactants and all the products are shown in their neutral, undissociated form. Then from there, we wrote the complete or total ionic equation. Here, all the strong electrolytes are written as dissociated ions, since this is the way that they actually exist in solution. All right, so anything with this aqueous label, we write in its dissociated form. This solid stays the same. All right. And then from there, we can then look to see what appears in both the reactants and the products. Those ions are spectator ions. We can eliminate them to then finally write our net ionic equation. So from removing the spectator ions, this will lead us to write the net ionic equation, which is the solution components that are directly involved in the reaction. All right. Silver cations, chloride anions give us silver chloride. Now, net ionic equations are very useful for three reasons. First, by removing all the non-reacting spectator ions, net ionic equations show clearly which species are actually reacting. Second, Net ionic equations help us see the driving force of a reaction. What is really causing the reaction to occur? Third, net ionic equations allow us to recognize the similarities among a large number of aqueous solutions involving electrolytes. Now, we want to build our knowledge here by extending into acid-base reactions, but we're going to leave that for the next lecture video. We're going to end here. I hope that this was helpful. Let me know if you have any questions, comments, concerns so far in our chapter 4. Other than that, good luck, happy studying, and have a beautiful, beautiful day.